Okay, so for this meeting, we're going to start a new topic, a new discussion. So we're going to shift gear into introduction to time series econometrics. So I think this is a very interesting topic on its own. And if you guys are interested in learning more about time series econometrics or macroeconometrics, there's going to be a course offered in the fall semester. So it's going to be a course on macroeconometrics. So it's going to be relatively advanced. However, I think for those who wants to do finance, who wants to do macroeconometrics, should definitely think about taking the time series econometrics. And so today, I guess the goal is to try to lay out the foundation on time series econometrics. And I'm going to provide you just a brief introduction on forecasting. So this is not a rigorous example of forecasting that you will see, in advanced finance model or like advanced time series model. However, with this particularly basic exercise in mind, you'll be able to do forecasting in the future. Okay. All right. So I'm going to start with the definition of time series econometrics and then time series data. So you can always, raise your hand if you have any questions related to the materials being delivered. Okay, so I'm going to start first with time series data, and we're going to go through all the important discussions for the day. And I'm going to go back and forth to Stata to provide you with an illustration of time series analysis in Stata. All right, so I'm going to start with the definition of time series. A time series is a collection of observations ordered across time. So we're going to use, say, a particular variable called y, and then we're going to use subscript t to indicate the time period for the data. So time series data is collected for a single entity at multiple points in time. So for example, if you're looking at, individuals, you're looking at communities, you're looking at firms, you're looking at districts, you're looking at regions, or for example, countries. And these are the example of data that you can observe. For example, monthly inflation rates of Indonesia for the past, say, 20 years. Daily exchange rate for the past year, or hourly stock index for the past month. So these are some example of time series data that you can see in available data set. And so the idea is that you have a single entity, and the entity could vary from individuals to countries. And then for that particular entity, you're going to observe multiple observations across time. And the time could be weekly, could be hourly, it could be daily, depending on the data set that you're analyzing. So let's go into more formal definition. So a time series process is a sequence of random variables indexed by time. So what you actually see, in the data. So for example, if you see an inflation rate of 0.69 in the past month, for example, it's actually a realization of a random variable. Okay. And so this is kind of like a formal definition of time series, and I'm going to provide you with a little bit more nuance in the subsequent slides. Okay, so let's go in and learn about some notations before I go back to the idea of the formal definition of time series. So the total number of observation for a particular data set is going to be capital T, okay? And then the current value is going to be denoted as y subscript t. We can also use previous values. So for example, in this particular case, yt minus 1 is going to be the value at t minus 1. T minus j will be the value at t minus j. Okay, so it's not obvious for everyone why we want to use a past values right now. However, I think for subsequent discussions and subsequent analysis, it's going to be clear why we want to include past values in the analysis. We can also learn about the future value. So for example, what's the value 1 period ahead? That's yt plus 1. What's the value 2 periods ahead? That's going to be yt plus 2, and so on. And another dimension that we want to know is the change in the value between period t and period t minus 1. So in this particular case, delta yt is going to be the difference between the observation that we see today and the observation at t minus 1. Okay, so these are kind of like the basic notations that you will use in the time series analysis. All right, I'm going to stop here for now. I'm going to give you a chance to ask questions or to clarify. Go ahead. Okay. Yes, go ahead.
Sorry, may I ask, what does it mean for the lag and the future value ones?
Yes.
Thank you.
Okay, sure. Yes, so when we do analysis, sometimes we're interested not only on the value today, but also on the value yesterday. And in some analysis, not only that we're interested in the value today, but the value in the future. Now, in that particular case, we want to also be able to identify the past values and the future values in the model. Now, again, it's not clear for now, but once we get into the data, I think it's going to be, clearer. Okay. All right. All right, so I'll continue for now, but I'm going to keep opening, opportunities for you to ask questions. All right, so going back to the past values, one of the notation that we may use in the subsequent analysis or the subsequent discussion is called the lag operator. This is also a operator that we're going to use in Stata. So basically, if you want to kind of like notate the previous period, you're going to use this lag operator. So LYT is going to be the value at t minus 1. Okay. And if you have a more general one, say LJ YT, this is going to be YT minus J. So this is the value at t minus J. Okay. So for example, if I have YT minus 2 and I have a daily inflation rate, and so the inflation rate in May 2021, that's a particular value. And then YT minus 2 is going to be the observation in March 2021. Okay. So that's the idea of lag operator. Again, it may not be clear to everyone why we're using the lag operator, but it's going to be clear in, I think, several slides. Okay. Another operator that perhaps we're interested in is the lag operator, the forward operator, as well as the difference operator. So I'm going to provide you with those notations quite soon in Stata. But before that, I just want to go back to the idea of random realization of a random variable. Okay. So suppose that the horizontal line is the time period, okay? And then the vertical axis is the value of y, okay? Now suppose that I have just 3 period. I have period t, t plus 1, and then t minus 1, okay? Now, this is one of the assumptions that we're going to discuss later on, but going back to the idea of random variable. So what's the characteristics of a random variable? A characteristic of a random variable, it has a distribution, okay? And so let me take a particular distribution. So suppose that this is the distribution of y at t minus 1. This is going to be the distribution of y at period t, and then this is a distribution of y and t plus 1. Now, my drawing does not reflect that these distributions are the same. However, the 3 distribution at t, t plus 1, and t minus 1 are intended to be the same, okay? So please be mindful of the drawing that I made. Now, in one particular time period, we're going to see a realization of this random variable. So for example, at t minus 1, this is the realization of y, okay? At t, this is the realization at period t, and then this is the realization at t plus 1. So basically, the observation that you see in a particular time period is a realization of a random variable, okay? So this is called the data generating process. The data generating process is something that we do not observe. However, this is something that we want to try to understand so that we can build a better model, we can build a better predictions and so on. But the idea is that a time series data or a time series process is a realization of a random variable, okay? All right, so I'm gonna go to Stata, but before that, I'm gonna provide you the opportunity to ask questions. Go ahead.
Sir, just to confirm.
Yeah.
So time series data is not random in itself, but it is the result of the random variables, right?
Yeah, so yes, time series data or time series observation is a realization of a random variable, okay? And then again, the random variable is going to vary depending on our analysis. It's going to be different from one context to the other. Yeah. Okay.
Okay,
good.
Thank you, sir.
Sure, very well. So I'm going to go to Stata now, and we're going to, learn about time series. So you have all the data, I believe, that you can download in Elo. So for this particular exercise, what I'm going to do is I'm going to use the CPI data. So the CPI data provides you with a data of Indonesian consumer price index from 1968 until about 2013. The data is not updated, but if you want to update it into the latest consumer price index data, I think that will be nice. Now, once we upload the data, it's not going to be particularly clear that this is a time series data. And so for that, we're going to do some, editing, okay? So the first thing that you want to do is to find a package, okay? So the package is going to be referred to as the TSM-KTIM, okay? So TSM-KTIM is going to allow you to actually create a time series variable, okay? So you can find TSM-KTIM, and then you can click the module. And then once you click the module, you can ask Stata to actually install the module for you. So it's taking some time, I think, to upload. So let's give it a couple of seconds. But the idea is that after you click on the module is going to ask you to install it if you haven't done so. Okay. So here you have a click here to install, and you can click the button, and then you can use the TSM TIM package to create a new time series variable. Okay, so I have it already in my Stata, but you can do it in parallel. Now, after we have the TSM-KTIM package, what I'm going to do is I'm going to use the TSM-KTIM package, and then I'm going to create a new variable, and the variable is called time, and it's going to start at 1968, month 1. So we're going to start in January 1968. Okay, so this is going to be the variable that we're interested in. Now, the good thing, after using the TSM-KTIM package, Stata sets the variable time as the time variable. And so this is a good way before starting any data analysis in Stata using time series, you want to declare the time series variable. Okay, so that's the first thing that you need to do when you do your time series analysis. Okay, all right. The next thing that you're going to do is, this is just for the sake of discussion. You can always graph the variable of interest. In this particular case, the variable of interest is going to be the CPI-all, or the consumer price index. Now, in Stata, the good thing is that it can do some advanced time series analysis now. So it's been developing quite nice in the past decade, I guess. And the package for time series analysis has been improving quite significantly. So it's been nice to see that development. And so what we can do is we can use the TS line package to graph the consumer price index. Okay, and from the graph you can see that there is a steady increase of consumer price index from 1968 until about 1998, 1999. That was when the monetary and the multi-dimensional crisis struck between 1998 and 1999, and then there is a significant jump around that time. And then after that, the consumer price index keep increasing. And what's interesting is that the rate of increase after the 1998, 1999 monetary crisis is much steeper than the increase in consumer price index before 1998, 1999. So that's an interesting observation on its own. Okay. All right. So this is a very just, a basic introduction of time series analysis using Stata. Again, we're going to revisit Stata many times in this discussion. In fact, I'm going to go back and forth between Stata and the slide just to provide you the intuition as well as the practicality of analysis in Stata. Okay, so for now, I'm going to go back to the presentation. And in the presentation, I'm going to continue our discussion on, this is the graphic of monthly CPI of Indonesia. And then this is a graphic of monthly inflation of Indonesia. Can anyone recall the method to calculate inflation? Anyone? Does anyone recall the method to calculate inflation should you have the consumer price index data? It's very simple, but just want to make sure that you guys understand. This is a very basic calculation. Okay, I guess I'm having issues with my internet connection, but I just want to repeat. Anyone wants to does anyone wants to provide how to calculate inflation given that you have the consumer price index data? Okay, so I guess
you can calculate it using change.
Can you repeat that, Zaki? I couldn't hear very well.
Yes, sir. I think to calculate inflation when you have CPI data is to deduct the prior year CPI and then divide the result by the previous year CPI, and then you multiply it with 100 to.
Okay, very well. So thank you, Zaki. Yes, that's one of the methods that we can use to calculate inflation rate. That's also a general method if you want to calculate the growth rate of a particular variable. So the first method is to use the observation today, YT, and then subtract with the observation in the previous period, YT minus 1, and then divide it by YT minus 1 multiplied by 100%. So that's one of the methods that we can do it. We're actually going to revisit the idea in several slides. However, before we go into that particular slide, I'm going to provide you with a brief discussion on continuous and discrete time series. Okay, so I'll start with continuous time series. A continuous time series observations are made continuously through time. So in practice, the variables take discrete set of values. Okay, and a discrete time series are measured at specific times in an equally spaced interval. So for example, daily, weekly, monthly, quarterly, and annually. So basically a lot of the time series observations or the time series data that you'll see is of the discrete time series, okay? Because you see it at an equally spaced interval, okay? So again, in practice, we observe discrete time series just because it's, we observe it in an equally spaced interval. Okay. Another reason is that data are recorded or sampled in specific time intervals. So for example, weather could be a continuous data, or like, when we talk about the temperature could actually be a continuous variable. However, it's actually recorded at specific time periods. So for example, it's recorded every 30 minutes, it's recorded every hour, stuff like that. And so if we're talking about stock prices, for example, we record, the hourly stock price. So we don't record it every seconds, for example. And for exchange rate, we don't necessarily record it every week, but we record it daily. And so these time series data are called flows. But we also have data that are aggregated in specific time intervals. So for example, a Q1 aggregate consumption is a consumption that is aggregated, consumption between January, February, and March that are aggregated into one quarterly aggregate consumption. And we also have the aggregate output, which is a, aggregate output, which is a combination of output within that particular quarter. Now, for this particular time series, is going to be called as stocks. Okay. All right. I think I'm going to continue on the growth rates since I already provide you with a brief hint on how to calculate growth rates. So basically, economists and then practitioners are very much interested in growth rates. You're interested in the growth of the economy, economic growth. You're interested in inflation rate. You're interested in the growth of assets. You're interested in the growth of house prices in a particular economy. You're interested in the growth of exports. You're interested in the growth of, or the change of exchange rate, for example. Now, how do we calculate growth rate? Now, this is actually very simple. This is actually very basic. However, in practice, surprisingly, a lot of the students are not aware of the method to calculate growth rate. So I just want to make sure that everyone who takes this Econometrics 1 course know how to calculate growth rate because that's going to be used over and over and over again. Okay. So I don't want you in a point where, you graduated and then you work in a particular office and you forgot how to calculate growth rate. I think that's going to be a pity. But just to make sure that you guys have all, the knowledge and then the practical skills to actually calculate the growth rate. So here we go. So basically, there are two ways to calculate growth rate. The first one is something that Zaki has mentioned before. So basically what you want to do is you want to calculate the difference between y at period t and then y at t minus 1. And then you're going to divide it with yt minus 1. Okay. In other words, you can have the delta YT divided by YT minus 1. So this is the first method that we can use. The second method is to use growth rate calculated using logarithmic growth. Okay. Now, before we want to use it, we need, we need to make sure that the observed variables are positive. Okay, since if you take a logarithmic of some of 1, it's going to be 0. A logarithmic of 0 is going to be undefined. And so here, if you want to use a logarithmic growth, you want to make sure that your observations are positive. So once you do your logarithmic transformation, the growth rate is quite simple, which is just the difference between log YT and then log YT minus 1. Okay, so it's very simple and it's very straightforward. The question is, will the two alternatives result in a similar number? The answer is no. It's going to produce a different number, but it's an approximation. So you can use either one. Either you want to use the growth rate calculated by delta YT divided by YT minus 1, or you can use the logarithmic transformation. It says you can use either of them. Okay. Again, if you're interested in knowing why the two methods are actually quite similar, you can go ahead and look at this particular graph. Okay. All right. I'm going to go to Stata and I'm going to provide you with a direct example of calculating growth rate, both using the first alternative and then using the logarithmic growth. But before we go there, any questions, please? Okay, great. I'm going to switch to Stata and I'm going to provide you with an illustration on how to calculate growth rate using available data. Okay, so since we have the consumer price index data, we can now calculate inflation. Okay, so basically, if you have a price index data, it could be a consumer price index, it could be a wholesale price index, it could be the producer price index. You can actually calculate inflation using those variables, although they're going to generate a different, measure of inflation. But let's start with the first method. Okay, so I'm going to generate inflation, which is the change in YT. Okay, so it's CPI period T minus CPI T minus 1 divided by L dot YT minus 1, which is CPI all. Okay, so this is the first way of calculating inflation. And the second one is to use logarithmic transformation. So before I do any calculation of the inflation, I'm going to generate LCPI, which is the logarithmic transformation of CPI all. And after I calculate the LCPI, what I'm going to do is I'm going to generate inflation. I'm going to name it as just INF in this particular case. And it's actually the change in the log CPI. Okay. Okay, I apologize. I think I have a very choppy connection, internet connection this afternoon. But yeah, I'm going to continue for now. And I'm going to try to make sure that the recording is done in the computer. So hopefully, you can always revisit the video again to make sure that you catch up on the important principles. But again, I apologize for the choppy connection. All right, so I'm gonna just go back to discuss about the second method to calculate the CPI. So we've done the first method, which is using yt minus 1 divided by yt minus 1. And then the second one is to use the logarithmic growth. So both methods are going to generate different numbers, but that's okay because those are approximations. So, you can use either one. It doesn't really matter. But I'm just going to provide you with an illustration of the inflation and then the INF, variables. Okay, so as you can see, whether you use the first method to calculate inflation or the second method to calculate inflation, it doesn't really make much of a difference. Yes, there will be some difference, but the difference is not going to be that significant. Okay, and so this is the way that we calculate inflation. And if you want to do a better graph, that's also possible. So for example, you want to do something more fancy just to make sure that all the information that is available are recorded into the data set. That's also possible. So let me see. In this particular case, okay. Okay, so in this particular case, you have two different measure of inflation, and what's interesting is that you have different time periods, and then there are periods where the inflation is high. For example, during the 1998-1999 crisis, we also see a huge spike here. So this is around 2005. This is when the government of Indonesia first announced that there is going to be a reduction in the fuel subsidy. And so a reduction in the fuel subsidy premium at that time, push prices to be higher, and thus the inflation. And so I think these are some interesting time in the past 2 decades. But there are also like huge inflation back in the 1960s and back in 1970s. That's also another dynamic that if you're interested in, history, you can go back and look at it. But anyway, that's the way that we want to calculate inflation, and something that, you can do from time to time. All right. So I'm going to go back to Stata. I'm going to back to the slide deck. But before I do so, any questions on the graphing and then calculation of inflation in Stata? Go ahead.
I'm sorry, sir, if I may, sir.
Yes, go ahead, Jovan.
I want to ask, what is the difference between DCPI and LCPI, sir, in the Stata, if I may? Thank you, sir.
Yeah, sure, definitely. So if you recall, in the previous deck, you have the lag operator, and then you have the difference operator. So a lag operator allows you to identify the past value. So LCPI means CPI at t-1. Okay, and then DCPI means it's the difference operator. It's the difference of CPI at t and then t-1. Okay, so that's the idea. So you have the lag operator and you have the difference operator. Okay, good. Any other questions, clarification? Okay, good. So I think I can continue into the basic techniques. Okay, so the first basic techniques that I'm going to discuss here is called detrending. Okay, all right. So before we do any kind of like detrending analysis, what I'm going to do is provide you with a illustration on the components of a time series data. So if you have a time series data, then a time series data is usually comprised of several components. The first component is going to be the trend. Okay, we usually just write it as the T. And then the second component is going to be cycle. Okay. And then the third component is going to be seasonality, or S. And then the fourth component is usually I, which is the irregular component. Okay, so when we talk about a time series, the time series usually has some of these components. Okay. Now the next questions in mind is when we want to do some analysis, sometimes we want to remove some of this component. Okay, so for now I'm going to focus on the first one, which is on the trend component and how do we remove the trend component. Okay, so it's actually very straightforward. So if you want to remove the trend component from the variable, the first thing that you want to do is you want to identify the trend. So the trend could be a linear trend. The trend could be a quadratic trend. The trend could be of some higher polynomial. Okay, so it could be a trend of polynomial degree 3, polynomial degree 4, and stuff like that, and many more. But again, in practice, usually it's going to be a relatively straightforward trend. Usually it's a linear trend or probably a quadratic trend. So I'm going to focus on a linear trend. So the way that we want to remove the trend is to regress the y variable on the trend itself. Okay. And then the residual of the regression is going to be called the detrended time series. Okay, so again, you have a time series, and then you have a a time variable, and then when you regress the time series on the trend variable, and then calculate the residual, then the residual is going to be the detrended series. Okay, so that's the idea of detrending. Okay, again, I'm going to go to Stata to provide you with an example of that. But before we go there, I'm going to go into the second component of time series. So recall that in addition to trend, there's also a seasonal component. And so in United States context, for example, there's that summer, fall, spring, and then winter. And the economic has different patterns depending on the seasonal, the seasons in effect. So for example, the demand for corn, for example, is seasonal. The demand for apple is also seasonal. In Indonesia, the seasonality is actually quite different. It's actually quite interesting. So we have the dry or the monsoon season. The dry or the monsoon season is going to affect the commodity prices, particularly agriculture commodities. And you also have big events such as the Eid Fitr, we have the Eid Adha, we have the Christmas, and then we have the start of the school year. So these different seasons provide you with a different, with a different economic dynamics, and it's actually recorded in the data. So it's actually quite important for us to kind of like identify the seasonal effects in our data. However, just to be very clear here, since Eid Fitr and Eid Adha moves every year, so it moves around 10 to 11 days every year. So you might want to have to adjust that year by year. Okay, so what can we do to accommodate seasonality in the data? The one way that we can do is to include dummy variables for each season. This assumes that the seasonality doesn't change over the sample. This is not particularly true for Eid Adha and Eid Fitr. And you can also do seasonality adjusted data. So again, seasonality adjusted data is sensible if the season doesn't change over time. Okay. And then you can use the seasonal operator in Stata to create the seasonally adjusted data. Okay, so these are the two examples that that we have, and I'm gonna go to Stata and then provide you with a brief sample on how to do detrending. Okay, any questions before I go into Stata? Okay. All right, so yeah, I'm going back to Stata, and then I'm going to provide you a illustration on how to do detrending. So the first thing that I'm going to do is I'm going to preserve the Okay, so we preserve the data set, and I'm going to keep if the observation is between 2000 January until the end of the data set. Okay, and so first thing before we do any detrending, the first thing that we want to do is just to look at the data. Okay, so the data suggests that the trend is a linear one, and so we can regress on a linear trend. Okay, so this is the way that we're going to do it. We're going to regress. Okay, the variable CPI all on the trend variable. So in this particular case, we can use the underscore end, and then sorry, actually, I'm going to generate a new variable first. Is the time period of the trend, which is the underscore n. Okay, and then I'm going to regress CPI all on the trend. Okay, so we don't really care about the regression results itself. However, we care about the two trended time series, and so what I can ask Stata is I'm going to ask Stata to calculate the residual. Okay, so the residual is going to be called the CPI the trend, okay, which is the residual of the regression. And so the residual of the regression is going to be the CPI detrend. Okay, and so this is one particular way of getting a detrended series. Okay. So the next one is, is the seasonal effect. So if you recall, the seasonality could change from time to time, but perhaps we can rely on a general pattern that we, studied since we were elementary school, that the dry season is going to be somewhere between the month of May until the month of September, and then the month of October until the month of April. It's going to be the month of monsoon season. Okay, so let's try to use that pattern, although again, the pattern changes from time to time, but for the sake of example, we're going to use that particular definition. So before I do that, I'm going to generate a month variable by extracting the month component of the time series called time. Okay, now once you look at the data, you can actually observe the month identifier. So this is January, this is February, and so on. Okay, now the next thing is I'm going to generate a dummy variable, which is the dry season. If the month is May, if the month is between May and it's between September. Okay, now after we do this, what we can do is we can control it in the regression if you want to control for the trend as well as control the seasonality. So for example, we can regress CPI all, okay, and then we can regress the trend as well as the dry season. Okay, now this is a way of controlling for the trend and controlling for the seasonality. In this case, is controlling for the dry season. Okay. Now you can also be more general. All right, fine. I don't need to distinguish between the dry and the monsoon season, but I want to control for the seasonality that occurs month to month. That's also possible. And so the way that you want to do it is you want to regress CPI all on the trend as well as on the month variable. So in this particular case, you have a general seasonal pattern across month that you control and you acknowledge in the data. Okay. Now, after you do this, then you can record the residual, and the residual will be detrended and deseasonalized data. And in this particular case, the definition of seasonal is going to be a monthly seasonal. Okay, so this is the idea of detrending as well as deseasonalizing. Again, deseasonalizing in the context of Indonesia may not be as straightforward as deseasonalizing in other contexts, but this is one particular example how we can do, the method to do deseasonalizing. Okay, any questions before I go into the slide deck? Okay, so I'm going to go back to the slide deck and go back to the slide deck, and we're going to discuss examples of time series regression. Okay. All right. So the first example of a time series regression is the static model. Okay. So consider time series data on just two variables, y and then z, and y and z are dated contemporaneously. Okay, so a static model is a model where you regress y on z. Okay, it's called a static model because we model a contemporaneous relationship between y and z. So z affects y contemporaneously in that particular time period. Okay, so in this particularly static model, a change in z at time t has an immediate effect on y. All right. So again, this is a very simple model, and then we cannot generalize that every model is a static model. Okay. In fact, in a lot of contexts, the model could be dynamic, but again, understanding that there is a simple static model is actually beneficial for us to understand a more complex and dynamic model. Also, to understanding the limitations of a static model will allow us to actually understand what's the value of the dynamic model when we go and discuss dynamic model. Okay, so an example of a static model will be the Phillips curve. Anyone recall what a Phillips curve is?
I think it's the relationship between output and inflation rate, sir, or unemployment and inflation rate.
Exactly. So output and inflation rate is going to be another relationship, but Phillips curve is, as you said, a relationship between unemployment and inflation. Okay, so in this particular static model, we assume that inflation has a contemporaneous relationship with unemployment. So the idea is that when firms hire more workers in the economy, unemployment goes down. But when you hire more workers into the economy, you somehow have to increase the wages. And so increase in wages is going to be reflected in the increase of goods and inflation. Okay. So this particularly static Phillips curve model assumes a constant natural rate of unemployment and constant inflationary expectations. Again, this simple model is used to estimate the contemporaneous trade-off between inflation and unemployment. Okay, So before I go into the dynamic model, I'm going to go to Stata, and I'm going to provide you with an example of a static model. Okay. In this particular example, I'm going to use the Phillips curve data. So, you can go to your data set repository, and then you can find the Phillips curve data. Okay. So again, before any time series analysis, what you want to do is you want to declare that the data set is a time series data set. So you want to use the TS set, okay, and then year. Now I'm going to do a static Phillips curve regression. So if I regress inflation on unemployment, if year is before and equal to 1996, and this is the relationship that you get. Okay, so based on the static model, the unemployment and inflation has a positive relationship. Does anyone recall, in theory, what's the relationship? Between inflation and unemployment? Is it positive or is it negative? Anyone recall? Okay, so I guess again, apology for my internet connection, but
I think it's inversely.
Yeah, it's inversely related. Very good, Matthew. So there is a negative relationship between inflation and unemployment. However, in this particular estimation, we actually get that inflation and unemployment are positively related. Okay, so it doesn't mean that, in reality, the relationship is positive as what the static model says. It could be the fact that, we're not formulating the model, precisely. We may be leaving out some dynamics that is important in the inflation and unemployment relationship. Okay, so we're going to hold on to this particular example. Okay, and then we're going to use it in a future discussion to show you that if we misspecify the model, we could get a relationship that is quite different with what is in the theory. Okay, so this is one particular example where specification matters. Okay, all right. So I'm going to go back to Stata, and then I'm going to continue into the second type model, which is the finite distributed like model. Okay, so recall we have the static model. Again, the static model has a lot of deficiencies. It has a lot of disadvantages. And so the alternative will be the finite distributed like model. So in this particular case, I'm going to discuss finite distributed like model of order 2. In this particular case, YT is going to be a function of ZT, ZT minus 1, and then ZT minus 2. Okay, so let's investigate how to interpret the coefficients of the finite distributed like model in the previous slide. Now, to do that, we're going to make some supposition. So the first one is that we're going to suppose that Z is a constant C in all times before T. Okay, and then at time T, Z increases by 1 unit. But then after it increases at T plus 1, after it increases in T, it's going to revert back to C at T plus 1. Okay, so for example, we have ZT minus 2 is C, ZT minus 1 is C, but then at ZT, it increases to C plus 1. And then at ZT plus 1 and ZT plus 2, it's going to reduce back to C. Okay, so the idea is that it's going to be C, and then it's going to jump to C plus 1, and then it's going to go back at C. So this is C, and then this is C plus 1. This is at time T. This is at T plus 1, T plus 2, T minus 1, T minus 2. Okay, so that's the idea. Now, we're going to assume that there is a ceteris paribus effect. So the value of unobservable is going to be 0. So recall that in yt minus 1, it's just going to be a function of the c's. At yt is going to be alpha 0, delta 0 c plus 1, delta 1 c, delta 2 z. Now, how do we get this? Recall that if you have yt minus 1, then this is going to be zt minus 1, zt minus 2, zt minus 3, and so on. Okay, so if you keep track of the subscript, you'll get this. Okay, so you should have to be patient and then keep track of the subscript, and then you'll know the difference. Okay, so you do that for all yt between yt minus 1 and then yt plus 3. And then after that, what you're going to do is you're going to subtract yt and then yt minus 1. So when you subtract yt from yt minus 1, so let's focus on here. If you subtract yt and yt minus 1, you can delete this, and then what you're going to have is just delta 0. Okay, so what does delta 0 shows? Delta 0 is the immediate change in y due to a unit increase in z at time t. Recall that there is a shock of 1 unit in time t for the zt variable. So delta 0 is the immediate change in y due to a unit increase in z at time t. So this parameter is called the impact propensity or the impact multiplier of z. Similarly, if you do yt plus 1, yt minus 1, yt plus 2, and then yt minus 1, you can actually get the change in y 1 period after the temporary change or the shock. And then this is the change in y 2 periods after the shock. Okay, so again, delta 1 is the change in y 1 period after the shock. Delta 2 is the change in y 2 periods after the change. And you can see that it goes back to normal. The relationship is the same after 3 periods. And so the sum of the coefficients on the current and the lag z, which is delta 0 plus delta 1 plus delta 2, is going to refer to as the long run change in y given permanent increase in z. Okay, and the sum is called the long run propensity or the long run multiplier. All right. So any questions before I go and discuss the example? Go ahead. Okay. All right. Good. So I'm going to provide you with a brief example, which is the fertility rate. So in such model, we allow one or more variables to affect y with a lag. Okay. So consider the general fertility rate, which is the children born per 1,000 women on childbearing age, GFR, and then PE is the real dollar value of the personal tax exemption. So you want to know whether a policy on personal tax exemption, so a policy on personal tax exemption is going to basically, reduce the tax payment that you have to pay to the government, and then you can use that for personal consumption or personal savings. In this particular case, we want to know whether the personal exemption policy is going to improve the fertility rate of people. So, if you give households, more savings through lower taxes that you have to pay, perhaps they're going to, decide to have more children. And so you want to see whether there is that effect. Now, if you think about it, if the government enact the personal exemption tax today, it doesn't mean that the fertility rate is going to contemporaneously increase in the same day. Okay, it's going to take some time. People decide to say to have another children. That's going to take 9 months, or it's going to take some time. And so the effect is not going to be contemporaneous. So an increase, personal tax exemption policy today perhaps will be, will affect the general fertility rate in the next year. So in this particular case, not only that we want to model something that is static, we also want to model that is with a distributed lag. Okay, so at least we want to say that the personal exemption policy that is implemented at T-1, it's going to affect the fertility rate today. Okay, or the personal exemption tax that was implemented 2 years ago has a effect of general fertility rate today. But we don't want to close any possibility that personal exemption tax that is applied today, or perhaps at the start of the year, could also affect the general fertility rate, which is recorded at the end of the year. Okay, so basically, this model analyzed whether the decision to have children is linked to the tax value of having a child. And the model suggests that decisions to have children will not immediately result from changes in the personal exemption tax. So it's actually going to take some time. So I provided you with the fertility rate data analysis that you can find in ELOC. So I'm going to ask you to have your independent learning and to go through the fertility rate example. And I think I'm going to stop here for a break. We're going to come back in 10 minutes, which is at 2:45 p.m. And we're going to discuss the key assumptions when we do OLS regression using time series data. And the assumption is called the stationarity assumption. This is going to be an assumption that you'll see over and over again, particularly those who are interested in time series analysis. So we're going to have a discussion on that. But before that, let's take a 10-minute break, and I'm going to try to make sure that the internet connection resumes to normal after we get the break. So let's go back at 2:45 and have a good break. Okay, so we're going to go into the stationarity and asymptotic properties of OLS. As I've said, this is going to be one of the assumptions, for us to do OLS regression. And stationarity assumption is actually a very important assumption that we need to fulfill to obtain a consistent estimate of the coefficients in the model. Okay, so we're going to start with what is stationarity, and then why is it important for us to fulfill the stationarity assumption. Okay, so again, the concept of a stationary process is an important topic in the time series econometrics. In fact, when you go and discuss when you do your time series analysis or time series econometrics or macroeconometrics, one of the things that you're going to discuss in maybe one or two particular meeting is the idea of stationarity, and then what would happen if you have a non-stationary data. Okay, so YT is stationary if its probability distribution does not change over time. So basically, YT have the same distribution as YT minus J and YT plus K for J and K equals to 1, 2, 3, and so on. So in other words, stationarity means that Y1, Y2 until YT are identically distributed. However, they are most likely not independent. Okay, so I'm going to provide you with, again, a brief illustration of stationarity. Suppose that this is the same graphic that we had. This is the time horizon. This is the Y. this is t plus 1, and then this is t minus 1. Okay, so stationarity means that y is going to have the same distribution across period. Okay, so again, the drawing is meant that the distribution are identical across time. Okay, and so this is the idea that the distributions are identical, identically distributed. So it has the same mean and the same variation. So that's the idea of stationarity. Okay, you know, one of the implication of having a stationary data set is that the data tends to move within, you know, a distribution, a particular distribution. That's something that, you know, we're generally interested in. Okay. However, if you have something like this, so I'm gonna create a new graph. Okay. Suppose that this is the time dimension, this is the y variable. Suppose that this is t, t plus 1, t minus 1. So suppose that you have a distribution right here at t minus 1, and then you have another distribution at period t, and then you have a distribution at t plus 1. That's an indication that the distributions are not identical across period. And so since the distributions are not identical across period, then they're more likely to be non-stationary. Okay. And so if you recall the Stata data, you look at the CPI, consumer price index data, and then you have the monthly inflation data. And you see the CPI data keeps increasing across time. So that's one indication that the CPI variable is not stationary. Okay. However, for the monthly inflation, the inflation you know, moves around a particular mean, and so that's an indication that it's actually stationary. Okay. Again, that's not you know, that's just a very informal way of looking at stationarity. You know, when you look at future time series econometrics course, there's going to be a formal test to see whether or not it's stationary, but you know, sometimes an informal data could provide us with a brief guess on whether the data is stationary or non-stationary. Again, this is an example of non-stationary data. We've looked at this previously. This is the CPI data that we have in our data set. And then this is an example of stationary data set. Okay, so an example of stationary data set is that it moves around a particular mean, whereas here there is no movement around the mean. So that's a very informal way of looking at whether a data is stationary or not. But you know, even the informal way of looking at it provides you with a good or brief example. Okay. Before I go and discuss why stationarity, any questions on the idea of stationarity? Okay, very well. So why do we need stationarity assumption when we do want to do our OLS regression? Stationarity allow us to implement the law of the large numbers and the central limit theorem. Okay, so recall the discussion of law of large numbers as well as the central limit theorem in the you know, in the statistics 2 course that you know, you just completed. So if we are to analyze, you know, variables, we want the variables to be stable over time or stationary. Okay. So let's go into the definition. So the definition of covariance or weakly stationary process. So it's rather long, but I want to focus on several key components of this definition. Okay. The first one is that it has a constant mean. It has a constant variance. However, the covariance between the observation that we see today and the observation that we see each period ahead is going to be a function of the length of age, okay? The relationship between observation that we observe today and then t plus h is not dependent on the time period itself, but it's just on how far away the observation is. So this is an example, or this is a definition of covariance or weakly stationary process. You have a same mean, you have the same variance, and so if you have the same mean and you have the same variance, you have identically distribution across time periods, okay? However, the observation that you observe today and in the previous periods could be correlated, okay? When you think of it as inflation, okay, the inflation today could be partially explained or affected by the inflation at t-1. However, the inflation today, may not be affected by the inflation 3 periods before or like 4 periods before. That's going to be different with the consumer price index, and we're going to provide you with an illustration of that. Okay. So basically, the covariance stationarity implies that two realizations, which is yt and then yt plus h, is going to be dependent. It's going to be dependent, or it's going to be correlated, and it's okay. So it doesn't break the stationarity example. Now, one thing to note is that the correlation between the realizations today and the realization at t plus h is going to have a correlation close to 0, okay? Or like the covariance is going to get to 0 as the length or the difference between the time increases, okay? So the further away the observations or the two observations, then they're more likely to be independent. Again, the example that I gave you is that the inflation today could be affected by the inflation at the previous period. However, the inflation today might not be affected by the inflation at a year before. So that's one example. Okay, so a weakly stationary sequence with such characteristics is asymptotically uncorrelated. So what does it mean to be asymptotically? So as the width or the difference in the observations get larger, the correlation goes to 0. So it's called asymptotically uncorrelated. Okay. So with the stationarity in mind, we're going to look at some asymptotic properties of OLS. But before we do that, okay. Any clarification on stationarity? Again, my internet dropped again. But yes, if you have any questions or clarification on the stationarity before I continue on the asymptotic properties of OLS. Okay. All right, so I'm going to continue our discussion on asymptotic properties of OLS. So the first assumption, the stochastic process or the time series process follows a linear model. So if you recall, the linearity assumption means that the parameters in the model are constant, and the process is stationary and weakly dependent. So it's stationary in the sense that it has the same mean, it has the same variance. However, it's more likely to be correlated. Okay, and then we want stationarity assumption because we want to use sample averages. Okay, and so recall that if you recall the first discussion in chapter 2, when we want to calculate the OLS coefficient, we need the sample averages. So the sample averages is valid only if we have a stationary variable. Okay, if you don't have a stationary variable, then the average is not going to be valid. Okay. The assumption too is that explanatory variable in the sample is not constant. So you want to, explanatory variable that is changes, the value changes, and not a perfectly collinear with other explanatory variables. So basically no perfect multicollinearity. And then the explanatory variable are contemporaneously exogenous. So this is an assumption that, if you recall, in the cross-section data, it's called the zero conditional mean assumption. Okay, so the assumption suggests that on average, there is no correlation between the factors that we do not observe and the variable of interest at period t. Okay, so this is called contemporaneously exogenous. So again, there is no variable that we do not observe that is correlated with the variable of interest. That's contemporaneously exogenous. If we fulfill this stationarity assumption, the linearity in parameter, and then variation in the variable x, and then there is no perfect collinearity and contemporaneously exogenous, then the OLS estimators are consistent. Okay, so when we do the cross-section data, recall that we have the idea of unbiasedness. Okay, now another properties of estimator aside from unbiasedness is consistency. Okay, now in this particular case, we're not using the unbiasedness property, but we're using the consistency property of a particular estimation or a particular estimator. So in this particular case, if you fulfill the first, second, and third assumption, then you're going to have a consistent estimator of OLS. Okay, so this is kind of like a analogy on the unbiasedness that we discussed for the cross-sectional data. The next assumption is the homoscedasticity assumption. This is relatively similar to the one that we discussed for the cross-section data. What's new is there is no serial correlation or there is no autocorrelation in the data. Okay, so this is the assumption that we need. So basically, no serial correlation means that conditional on observables. Okay, so conditional on observable, there is no correlation between the observation that we have today and the observation that we have in the previous periods. So that's the idea of no serial correlation or no autocorrelation. Now, in time series econometrics, this is going to be the assumptions that is going to be violated most of the times. That's why we're going to have a specific discussion on serial correlation in our next meeting. Okay, so in our next meeting, we're going to discuss what would happen if the no serial correlation assumption or the no autocorrelation assumption is violated. Okay, if you relax that assumption, what do we need to do? What are the solution and what are the consequences? Okay, so that's something for the next lecture. So basically, if you fulfill the first assumption, second assumption, third, fourth, and fifth assumption, your OLS estimators is going to be consistent and it's going to be efficient. Okay, and if you include the OLS estimators as asymptotically normally distributed, then the OLS standard errors, the T statistics, F statistics are all asymptotically valid. Okay, so recall the idea of asymptotic is that as you increase the number of observation if you have in the data, then that's called the asymptotic nature. Okay, all right. So again, in this particular course, we will conduct time series analysis using only stationary data. In macroeconometrics, you will learn how to identify non-stationarity, test stationarity, and then do analysis using non-stationary data. Okay, which is, in a lot of cases are very much exciting, but you'll get there. But before that, we're just going to assume that the variables that we use are stationary. Okay. All right. Any questions on the idea of stationarity? Why do we need stationarity and so on? Go ahead. Okay, good. I guess that's going to be on stationarity. The next discussion is introduction to forecasting. Again, this is a very basic forecasting methodology. This is a simple forecasting just using the trend. And recall that in time series data, you have the trend component, seasonality component, you have the cycle component, and you have the irregular component. If you wanna do a better forecast or better predictions, you wanna identify each component of the time series. But for this particular case, we're just gonna focus on the trend component. Okay, so it's not gonna yield a good prediction or a good forecast, but it's gonna lay out a foundation for you on how to do forecasting in general. Okay. So again, just to recall what I said, time series component include trend, cycle, seasonality, and the remainder component or the irregularity component. So you can have additive decomposition. Okay, so basically it's a component of trend, and then cycle, seasonality, and then the remainder component, or you can have a multiplicative one. Okay, so basically Y is a function of the trend multiplied by the cycle, multiplied by the seasonality, and the remainder. And if you take a logarithmic transformation, then you'll have that the log YT is the log trend, log CT, log seasonality, and then the log remainder. Okay, so again, this is going to be the ideal forecasting scenario, but for this particular case, I'm just going to focus on the trend component here. Okay, so let's focus on using the trend, and basically we're going to assume additive decomposition. Okay, basically YT is going to be a function of the time trend, which is the capital T of T. Okay, so if you look at this particular specification, what you want to do is just you're going to regress the CPI on just the trend. Okay, and then use the result of the regression to predict the future trend. Okay, so we will learn two types of forecasts. The first one is called the in-sample forecast. So basically you forecast using the data that you have. And then the second one is out of sample forecast. So basically you're forecasting out of the sample. So for example, today is May 2021. So given the model, you wanna estimate what's the value of inflation in April 2021. That's called in-sample forecast. However, given the model and given the data that you have, you want to predict what's the inflation rate in June 2021, July 2021. That's going to be an example of out-of-sample forecasts. Okay. Now, in future courses, you will learn a more complex forecasting strategy that also includes a validation period. Okay, I'm not going to show you here, but the idea is the following. So suppose that this is your in-sample forecast. So this is your in-sample. And so what you're going to do is that if you want to do a validation period, you want to just keep a subsample, for model prediction. And then given the model, the estimation of the model, you're going to keep some sample of the data to use as a validation period. Okay, And so in this validation period, you can compare different forecasting methods, and then you're going to identify which from these forecasting models yield the best result, okay? Or basically which one is the best forecasting. And once you're confident that you have the best forecasting model that you can have, given the data and given the model, then you can extend the data to do out of sample forecasting, okay? So for today, I'm not gonna discuss validation period because our model is very, very simple. It's just a model with forecasting with trend. But if you have a more complex model, you can use this particular strategy to test which of the forecasting model is the best. And then given the best model, we can use it to do the out of sample forecasting. So again, forecasting tools have developed so significantly in the past 3 decades, even in the past decades. And given the computational capabilities of computers today, you know, forecasting is getting more and more ubiquitous. So again, if you're really interested in this, you should really dig deeper into this. You can learn about the computer programming of forecasting with R or with Stata. All of them are great, but the idea is just to start, okay? All right, so I'm going to show you in Stata, but this is the idea of in-sample fit, and this is the idea of out-sample fit. Okay, so given the data that we have, how can we predict consumer price index in the next few months, for example? This is an idea of forecasting. So for example, if you're looking at, okay, I'm interested in GDP, you know, given the pattern that we have today, what's going to be the value of GDP in the next, in the next quarter or the next 2 quarters, for example? That's something that you can do, okay? Again, not only that we care about point forecast, but we're also interested in looking at interval forecast. Why are we interested in looking at interval forecast? We're interested in looking at interval forecast because of the random nature of time series variable, okay? And in this particular case, not only that we care about the point interval, but we're also interested in looking at the interval, sorry. Not only that we're interested in the point estimate, this is the point estimate, but we're also interested in looking at the interval estimate, okay? So this is something that we're interested in. So this is the idea of forecasting. Any questions before I move on into Stata? And I'm gonna provide you with a very brief example of forecasting using trend. Go ahead. Okay, good. All right. So for this particular exercise, I'm going to go back to our CPI data, and then I'm going to use the same, you know, I'm going to use the same steps that we just did before, and so I guess I can skip those steps. So the first one that I'm going to do is I'm going to keep the sample. So I'm going to keep the sample if it's between January 2000 until the end of the data set, okay? So the first thing that I'm going to do is I'm going to do in-sample fit or in-sample forecast, okay? So it's actually quite straightforward. I'm just going to regress CPI all on the time variable, okay? And then I'm going to use the predict CPI fit to get the in-sample forecast, okay? Now, at the same time, I'm also going to predict the error, which is the residuals. All right, so this is going to be what's called the in-sample fit, okay? So basically, the black line is going to be the CPI data. It moves around every time depending on the actual realizations of the consumer price index. The blue line is the in-sample fit. This is the forecast if you use a model with just the trend. Okay, so a forecasting model with just the trend is quite good in identifying, the general, the general movement of the consumer price index, but it doesn't capture kind of like the movement along the trend. Okay, and so that's why you will need a more complicated model than just including the trend in the data. Okay. Now we can also do out of sample forecast. So for example, if you want to do out of sample forecast, the first thing that you want to do is, of course, you want to add the data. So for example, you're going to add, say, 12 months. Okay. And then you're going to use the data to predict P. Okay. It's a variable P if it's between 2000 and the end of the period. Okay. So now you have the okay. So you basically have the CPI today, and then the point forecast as well as the fitted values. Okay. So this is an example of out of sample forecast. So as you can see, the black line is the actual CPI line. Okay, so that's the realizations that we see. The green line is going to be the in-sample fit. And then the blue line is going to be the out of sample point forecast. Okay, so that's the idea of out of sample forecast. Now, again, just up until this particular point, we have just the in-sample forecast. Now, what we're interested in also is, the idea of forecast intervals. So the forecast intervals will provide us with some idea on how the data will fluctuate around the trend, for example. Okay. Now, this is a bit advanced, but I'm just going to provide you with, just the idea. Okay, so I'm going to use what's called the quantile regression. So the quantile regression of the error, okay, it's going to provide you with an estimate of, the forecast interval. In this particular case, I'm going to use the lower bound, which is the 5th percentile. Okay, and then you're going to predict Q1, and then you're going to generate CPI L, which is P, which is the point forecast, plus Q1. Okay, and then you're going to predict P1 if time is after. Okay, so apology for the bad internet connection. But again, the idea is that you have the forecast interval. This is for the lower bound. And then after this, you also have the upper bound. So how do you calculate the upper bound? You're going to use the same quantile regression for the period. And then you have 95 percentile. Okay, oh, sorry, 0.95, which is the percentile. And then you're going to predict, in this case, you're going to predict Q2, and then this is going to be your upper bound. So you're going to generate CPI H, which is P plus Q2. And then you're going to predict P2, which is time after time 2013, M4, okay? So this is the idea of generating out of sample forecast. So not only that you generate the out of sample forecast, but you also have the upper bound and then the lower bound for the estimation. So in this particular case, the black line, the black solid line is the actual CPI. So the actual data that you see. And then the blue line is the out of sample forecast. So this is kind of like the forecast that you're interested in. And then you have the upper bound, and then you have the lower bound. And the upper bound and the lower bound is going to provide you with kind of like the interval forecast. The idea is that, okay, given the past, residuals of the forecast, then this is going to be the range in which we're going to expect the actual observations. And so this is kind of like the empirical forecast interval using the 95% interval. Okay, so this is a very brief, very basic and very naive forecasting model. Why is it naive? Because we're only using the trend and we disregard any other information such as the seasonality, although we can include the seasonality component if we want. We also disregard the cycle, and we disregard the remainder component or the irregularities as well. But hopefully with this particularly simple forecasting model, you'll be able to understand the idea of, oh, we have in-sample forecast, we have out-of-sample forecast, and we also not only have the point forecast, but we also have the interval forecast for the data. So I guess it's going to set you up if you're interested to do time series modeling in the future. So hopefully it's going to generate some interest out of everyone. All right. So I guess that's going to be on forecasting. Any questions for the forecasting? Okay, if there is no question, okay. Yes, go ahead. Okay, go ahead, Matthew.
Okay, just to clarify, sir, regarding the in-sample and out-of-sample, would it be correct to say that when you use in-sample forecasting, you're trying to fit or forecast an observation that is part of your initial sample? And then when you use out-of-sample, you're trying to predict values for observations that were not included in your initial sample.
Yeah.
Would that be correct, sir?
Yeah. Yes, that is correct. So basically, if you want to predict, the value in the future, that's going to be exercise of out-of-sample forecast.
Okay, thank you, sir.
Sure. Okay. Any other clarifications or questions regarding forecast? Okay, good. Thank you so much for attending today's lecture. It's good to have everyone back. Again, our discussion next week is to try to understand what would happen if there is a serial correlation or autocorrelation. I think that's going to be interesting. So keep that in mind. I already have the materials uploaded into ELOC for next week lecture. I'm also going to upload the materials that we have today in YouTube, just in case you have to go back to the video notes. I think the internet connection today was quite choppy, and so I guess you had a lot of interruptions during the lecture. I apologize for that. I'll try to make sure that the internet connection goes back to normal in our future meetings. But all in all, you can review back the lecture notes that I will post later today. Have a good day, and I'll see you next week, same time, 1:30 p.m. sharp, and we're going to discuss the notion of serial correlation. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.